So this is going to be the notes on Riemann sums, and in the last notes we talked about the integral of f of dx, meaning the area under the curve of f of x. And so really we have two cases for this. And case one is we're just going to use geometry to compute this area. So if we have a problem like the integral from 1 to 4 of the absolute value of x minus 1 dx, then we'll go ahead and graph that. And the function is basically the v shape from the absolute value, and it's shifted. Remember, inside means we shift it 1 to the right. And so we're going from 1 to 4, and I said these are our x values. They match up with dx. So we're going from x is 1, this spot here, to x is 4, and it's the area underneath here, which will become a triangle. So the base is 1, 2, 3, and the height is also going to be 3. And the area for a triangle is 1/2 base times height, and so we'll get 9/2. And that will be our integral. So that basically the integral from 1 to 4 of the absolute value of x minus 1 dx is equal to 9/2. And case 2 is going to be if we have a curve or any other shape where we can't do geometry. So for example, if I wanted to compute the integral of x minus 1 squared dx, if we graph this, it's a parabola shifted, again, 1 unit to the right, and we want the area from 1 to 3, so from 1 to 3. So we want this area right in here. And that's not a nice shape. That's not a triangle. It's not a, it's not a normal shape that we can use geometry to calculate the area of. Later on, we're going to figure out, we're going to compute how to do this more precisely, more accurately. But for right now, we're going to employ some approximations, and the first one of these is called a Riemann sum. And what a Riemann sum does is it approximates the area under the curve or an integral. And so the way we do this, and again, just be careful, this is an approximation. So we're approximating this area under the curve. So our answer is not going to be exact, and we're just getting as close to as possible for right now. And so what Riemann basically found out is, okay, this is a, this area here, we don't know what it is necessarily, but we can approximate this. We can kind of say, okay, if I start up here and I move over, I do know the area of that rectangle. Now that's not going to be a good guess, that's going to be kind of inaccurate. So what he did is instead, he split it up into a bunch of tinier rectangles. So he said, okay, I'll put a dot there, and just make all these points. And then from there, I can split these up into a bunch of tinier rectangles. And, that can, all of those areas, if I add those up, it'll be a lot closer. Now notice that it's still not exact. In this case, we still have kind of these extra little pieces right here. So this will be what's called an over approximation. Our answer is going to be too high. But it gets us close enough so we're a lot closer to the integral. And so what Riemann sums always do is they break up the curve into a series of rectangles. And then we know the formula for a rectangle, the area is just base times height. And so we use a series of rectangles to add up, types of Riemann sums. And the first one we're going to talk about is the left-hand Riemann sum. And the reason it's a left-hand, so if we were trying to find the area of this integral, we are going to start breaking up, from -2 to +2. We're going to break it up into rectangles. And like I said, that would be one rectangle. If we wanted to make it into 2 rectangles, we could go 2 rectangles here. But you kind of have 2 options. You can say, okay, I want to make this rectangle starting from the left side, or you could have said, I want to make these rectangles starting from the right sides. And then there's actually going to be a third option, which is we're going to make the rectangles starting from the middle and going out in both ways. And so that's kind of the 3 Riemann sums. So for the left Riemann sum, we're always going to start on the left side. But you don't know how many rectangles to make. So each problem we say we're going to call this n, as in the number of intervals. Okay, intervals are basically how many rectangles are you going to do. So if I said I want to approximate this with 4 intervals, that means I want to have 4 rectangles. The more rectangles you make, the smaller, like if you make a ton of small little rectangles, it gets more and more accurate as you increase n. So in this case, if we did 4 intervals, okay, I'll start over here, and we have to figure out how wide each one is going to be. So to figure out how wide they're going to be, we have to say these endpoints, we're going to call this one B and A, and our width is going to be equal to B minus A. That's the distance, that's like the total distance, divided by n. So in our case, B minus A would be 2 minus negative 2 divided by 4. That becomes 4 over 4, or just 1. So the width of each one of these is going to be 1. So I know that's the width, and I'm going to start here on the left and move over. That's my first triangle. Now how would we get the height? So we know the width was 1. How would I get the height? It's just going to be f of negative 2. Then I make my next rectangle. And now I'm going to start here at negative 1. I'm going to move over 1. And this height is going to be f of negative 1. And you keep just repeating this process over and over again. And so, now we have this is, the height is f of 0. And then lastly we have a height of f of 1. And notice we never got to this final end one. We don't use that 2. So on a left-hand Riemann sum, we only use the lefts, negative 2, negative 1, 0, 1, and we don't use that very final point because we're using all the left sides. And all of these widths are 1. And so basically what we're doing is we're just doing area equals base times height. But if you notice, the base is always the same. So really it's going to be 1 times f of negative 2 plus 1 times f of negative 1 plus 1 f of 0 plus 1 f of 1. And since there's a 1 everywhere, that width is everywhere, you can factor it out. So when we get into an actual formula, okay, what our formula is going to be, it's going to be that the left-hand Riemann sum is equal to, remember, base times height. The base was B minus A divided by n, times the heights are all of our y values. So we call the first y value f of x0 plus f of x1, and you just keep adding all of your y values until you get to f of xn minus 1, and that's our formula. Now to go over just some of these terms, right, we said n is the number of intervals, b is our, and a are both our endpoints, and then f of x0, that's going to be our first y value, and then f of xn minus 1, this is actually the second to last y value, and we don't use the last y value for a left hand. Okay. Right hand is going to be the same thing, except now instead of starting off at negative 2, we start off on the right side. So we start off at negative 1 and we go over the other way. We start off at 0, go over, start off at 1, go left, and start off at 2 and go left. So this is just a little bit different. The formula ends up being the same, but the only change in the formula for a right-hand Riemann sum is that we get b minus a divided by n times, now see how our y values are going to be all of these right sides. So now we're not using our starting point. So it's f of x1, which is actually the second point, plus f of x2 plus, and we keep going, f of x n minus 1, but then you go all the way to the end at n. So everything's the same, but this is just going to be our second y value, and then this is our last y value. And finally we have the third one, which is the midpoint Riemann sum. And on this one, you go in the middle of negative 2 and 1, and you go to the left and to the right. Then you go in the middle of negative 1 and 0, you go to the left, to the right, middle of 0 and 1, left, right, and then the middle of 1 and 2, and you go left and right. And so this formula, our area is still the same, but it's going to be b minus a, sorry, our width is still the same, times, now the y values are, wouldn't this be y at negative 1.5, y at 0.5? So the way you calculate these is you just take the average of each of those. So it's just f of basically x to the 1/2 plus f of x to the 3/2 plus, and you keep adding up until you get your final point is going to be, remember this is n minus 1, so it's f of x to the point that would be n plus n minus 1 divided by 2, and then that just becomes, right, 2n over 2 minus 1/2, so it just becomes n minus 1/2. So you start off at a half, you finish at 1/2 less than n, and that's that formula. So all three of these are different formulas for Riemann sums. We'll do a couple examples in class. This video has been kind of long, so just make sure you have notes on these. Write down these three formulas. Make sure you have each of the three written down. If you need to go back at all, go back. I'm going to put the formulas up one last time, but we need to have each of these three formulas written down for tomorrow's class. And then there is one last approximation, and we're not going to go through it in detail, but it's called the trapezoid approximation. And it's not a Riemann sum, but what it does is you basically take each one of these and you turn it into a trapezoid. So instead of making it into a rectangle, it's a trapezoid. So it's not a Riemann sum because it's not a rectangle, but it does approximate very well. The formula is pretty complicated. So the formula is b minus a divided by n times. Now if you notice, we're going to use the height for this first one just once. So we'll use that base and the second base, or sorry, height. But then the second one we'll use for the left triangle and the right triangle. So what happens is it's f of x0 plus 2 f of x1 plus 2 f of x2 plus 2 f of xn minus 1, and then plus f of xn. So basically everything except for the two starting and the finish are doubled, and then you have to divide everything by 2. And you can, instead of dividing everything by 2, you can just move that 2 up here. Now this formula is a lot different than these three, and I have a really good shortcut that I like to do is, instead of memorizing this, normally if you have to do a trapezoid, you've already done a left and a right, and the trapezoid formula is actually equal to your left hand Riemann sum plus your right hand Riemann sum divided by 2, and this is a much better formula to remember.